Earth wasn't the solar system's first attempt at making a planet. Before Earth existed in any form that could hold atmosphere, support rotation, or maintain a stable orbit, other planetary configurations formed here. They accumulated mass. They developed gravity wells. Some likely had surfaces. None of them lasted. The solar system didn't produce Earth and stop. It produced planets, lost them, and kept going. What we call Earth is what remained after earlier configurations failed to persist. The solar system is roughly 4.6 billion years old. That age comes from radiometric dating of meteorites, fragments that haven't been reworked by planetary processes since the disk collapsed. But that 4.6 billion year mark doesn't represent a single formation event. It represents the point where enough material had condensed to leave isotopic signatures we can still measure. What happened before that condensation is harder to track. What happened during the first few 100 million years after it is even harder. The early solar system wasn't stable. The protoplanetary disk, a gas, dust, rocky fragments orbiting a young star, was still dense enough to influence orbital mechanics. Planets that formed in that environment didn't form into the configuration we see now. They formed, migrated, collided, and in some cases, stopped existing as distinct objects. We don't have direct observations of those lost planets. What we have is evidence that the current planetary arrangement can't be the first one. The orbits don't fit. The mass distribution doesn't fit. The compositional gradients across the inner solar system suggest objects formed in one location and ended up somewhere else, or didn't end up anywhere. Forming a planet is not the same as forming a world. A planet is mass. It's gravitational coherence. It's an object large enough that its own gravity pulls it into something close to a sphere. That threshold is low. You can meet it and still have no atmosphere, no geological activity, no capacity to maintain those things over time. A world requires more. It requires that the object persists long enough for systems to develop on it. Persistence isn't guaranteed by size. It's not guaranteed by composition. It's determined by whether the configuration, orbit, rotation, internal structure, remains stable across repeated physical stress. The early solar system applied that stress constantly. Gravitational interactions between forming planets could destabilize orbits. Material still falling inward from the disk could add mass asymmetrically. A close pass between two large bodies could eject one from the system entirely, or send it into the sun, or break it apart through tidal forces. The question isn't whether planets formed here before Earth. The evidence suggests they did. The question is why none of them persisted as worlds. If this approach, testing assumptions about planetary origins against physical limits, makes sense to you, hitting like signals that. It's a small action, but it keeps the analysis moving. Planetary formation in a protoplanetary disk follows a process called accretion. Small particles collide and stick. Those clusters collide with other clusters over time. If the collisions don't fragment the growing body, it gains enough mass to start pulling material in gravitationally rather than just through impact. In the inner disk, where temperatures were high enough to vaporize volatile compounds, rocky planetesimals formed first. These were objects ranging from a few kilometers to a few hundred kilometers across. Models suggest there may have been dozens of them, competing for the same reservoir of material. When two planetesimals collided, the outcome depended on velocity and angle. A slow, glancing collision could merge them into a larger body. A fast, head-on collision could shatter both. Some of these collisions likely produced objects large enough to qualify as planets, planetary embryos with enough gravity to begin differentiating into core and mantle. But size alone didn't stabilize them. If an embryo formed in a region where orbital resonances with Jupiter were strong, its orbit could stretch into an eccentric ellipse, bringing it close to other bodies. Close approaches either resulted in collision or gravitational scattering. One model, known as the Grand Tack Hypothesis, suggests Jupiter migrated inward early in the solar system's history, then reversed and migrated outward again. If that happened, it would have destabilized every planetary orbit in the inner disk. Objects that had been in stable circular paths would have been pushed into crossing orbits. Collision rates would have spiked. Some embryos would have accreted into larger bodies. Others would have been destroyed entirely or ejected. This process, formation interrupted by migration, collision, or ejection, didn't happen once. It happened repeatedly. Each time a large embryo formed, it changed the gravitational landscape. Each time one was destroyed, the debris re-entered the accretion process. There's no clear count of how many planetary configurations existed before Earth. But the isotopic composition of meteorites suggests at least several chemically distinct reservoirs of material mixed and separated multiple times. A planetary embryo roughly the size of Mars, call it a protoplanet, orbits in the region where Earth would eventually form. Its orbit is slightly elliptical, not perfectly circular. Over a few 100,000 years, that ellipse stretches further due to gravitational perturbations from Jupiter. The orbit begins crossing paths with another embryo of similar size. One orbit, they pass within a few planetary radii of each other. Tidal forces pull material off both surfaces, molten rock. Because both objects are still hot from accretion, the debris forms a temporary disk around the larger of the two bodies. A few orbits later, they collide. The impact doesn't destroy either object completely, but it does melt both. The cores merge. The mantles mix. Some of the molten material escapes into orbit. The rest settles into a new, larger body with a different rotation rate and a different orbital path than either of the original embryos had. But that new path crosses Jupiter's orbital resonance zone. Over the next few million years, the resonance stretches the orbit again. This time, the embryo's path brings it too close to the Sun. The surface heats beyond the point where any crust can solidify. Atmosphere, if there was one, is stripped by solar wind. The object doesn't explode. It just stops functioning as a discrete planet and begins losing mass to evaporation and tidal erosion. Eventually, what's left either falls into the Sun or breaks apart into fragments that re-enter the disk. Subscribing to this channel isn't about following individual videos. It's about aligning with a way of thinking about planetary processes that continues beyond any single explanation. At some point, something in the inner solar system stopped resetting. Not because the physical stresses disappeared. They didn't. Jupiter's migration likely ended, which stabilized outer orbits and reduced the frequency of resonance disruptions in the inner disk. The protoplanetary disk thinned as material either accreted into planets or was cleared by solar wind. Collision rates dropped because fewer planetesimals remained. In that slightly less chaotic environment, one of the planetary embryos that formed managed to stay in a configuration that didn't immediately destabilize. Its orbit didn't cross resonance zones that would stretch it into an eccentric path. Its mass was large enough that smaller impacts added material without fragmenting it. Its rotation, likely set by the last major collision it experienced, was fast enough to prevent tidal locking, but not so fast that centrifugal force destabilized it. This wasn't Earth yet. Earth's current mass, composition, and orbital parameters were still being set by processes that would take tens of millions more years. But it was a proto-Earth, a body in a location and configuration that allowed it to keep accreting without being destroyed or ejected. What made that configuration work wasn't a protective mechanism. It was timing. The object formed after the most violent phase of planetary migration had ended, but before the remaining material in the disk had been completely cleared. It was massive enough to dominate its orbital zone, which meant fewer large competitors that could destabilize it through close encounters. Other embryos likely existed at the same time in different parts of the inner disk. Some of them probably survived the early instability period as well. But they didn't all remain where they formed. Evidence from isotopic anomalies in Earth's mantle suggests that at least one other large body, likely Mars-sized or larger, collided with proto-Earth after both had partially differentiated. That collision would become significant later. But at this stage, the key fact is that proto-Earth absorbed it rather than being destroyed by it. That's not success. It's just a longer duration between resets. We don't know how many planetary configurations existed in the inner solar system before Earth. The evidence for lost planets comes from indirect sources, isotopic ratios in meteorites that indicate chemically isolated reservoirs of material, orbital simulations that require more mass in the early inner disk than currently exists there, and compositional mismatches between planets that suggest they didn't all form where they are now. But isotopic ratios don't tell us how many discrete planets those reservoirs formed into. Simulations allow a range of outcomes depending on initial conditions, migration timing, disk density, collision velocities, and we don't know which set of conditions matches what actually happened. Compositional data tells us material moved, not how many times planetary-scale objects formed and failed before the current configuration stabilized. What we can say is this: the early solar system had enough mass and enough orbital instability to form and destroy multiple planetary configurations before the current one stabilized. How many formed, how long each lasted, and how they were destroyed varies depending on which reconstruction you follow. If the idea that the solar system's planetary history is still unresolved creates friction, good. That friction sharpens when it's shared. When someone else examines the same incomplete evidence and argues for a different interpretation. Sharing this kind of unresolved scientific tension isn't about agreement. It's about making the limits of current models visible. The solar system didn't fail to make worlds before Earth. It made planets. Some of them were large. Some probably had differentiated interiors. A few may have lasted millions of years. What they didn't do is persist long enough to qualify as worlds under the definition that matters here. They formed. And then the system reset them. New configurations replaced old ones. Mass was redistributed. Orbits shifted. Earth emerged from that process not because the system designed it, but because the configuration that became Earth happened to form during a period when the mechanisms that had destroyed earlier attempts were no longer dominant. But that raises a problem. If Earth's persistence wasn't guaranteed by the system that produced it, if earlier configurations with similar mass and composition failed to last, then Earth's survival required something more than just forming in a slightly more stable environment. It required that the instabilities still present in the early solar system, the ones that continued to affect proto-Earth after it stopped resetting, didn't destroy it before it could finish accreting. Something disrupted that process. Not in a way that stabilized Earth immediately, but in a way that changed the probability distribution. That disruption wasn't gradual. It was sudden, catastrophic. And it happened at a scale large enough to alter Earth's internal structure and orbital mechanics simultaneously. If you're left with the sense that the current explanation isn't sufficient, that forming in a less chaotic period doesn't fully account for Earth's survival, comments are where that insufficiency becomes explicit. They don't resolve the tension. They document it.